Hey folks, welcome back. Uh, we're going to be starting the second module, which is really the foundation and framework for a lot of the geospatial technology that we're going to be using in this class. This is in module two, and there are two functional pieces of this, map projections and coordinate systems. So the purpose of this is really to answer the questions: where am I? What is my position on the Earth? How can I use that to navigate? And how can I use that to represent locations on maps? Working from the sphere that the Earth is, a oblate spheroid, projecting these three-dimensional coordinates or locations onto maps that we can use more or less in 2 dimensions is kind of the background here. So I'm simply opening the story map here, and I won't go through it laboriously, but I do want to point out highlights. So this is actually the clip that I'm going to be providing you to kind of walk you through this. The circumference of the Earth was first really measured, and quite accurately, within to about 3% of what we would consider a measure today, by the Greek scholar and polymath Eratosthenes. And this was noted, the Greeks certainly had believed that the Earth was a sphere, but they actually used a unit of measure called the stadia. And they measured the distance between two, at the time, sort of centers of learning. You may have heard of Alexandria in Egypt and the city of Siam. They had noticed that at the peak of the sun, solar noon, that the shadows cast by the sun were different in these 2 different locations. And so that angle provides a measure of using simple geometry to estimate that angle or that arc on the surface of the Earth, which then you can derive the actual total circumference. So that's kind of the genius behind the early Greek mathematics and geographers. Next is representing Earth on maps. Certainly this process we call projection, projecting from a sphere to a surface or flat map. We really have 3 types of flat maps we can use: 3 projection, developable surfaces, they're called, planes, cones, and cylinders. So here's a video that I'd like you to watch. It kind of illustrates that, kind of attempts, and why all maps essentially are wrong and have some degree of distortion or error. The next is a little section here about the geometry, that the Earth is not a perfect sphere. It is kind of squashed at the poles. It has, certainly centrifugal force acting on it by its rotation. So it's basically, if you took a basketball and you pushed down on the top and bottom, and you had kind of about a 3% kind of bulging at the equator, that's what you would approximately have with the Earth. And so we have to project locations on a sphere onto one of these 3 type of flat surfaces. Now, they're not flat when they're shown here as like a cylinder or a plane, but you can unfold those and to create a flat 2-dimensional map. And then you can measure different types of coordinates on it. So here's a graphic that kind of better illustrates, maybe it's an old one, but a flat planar projection, what's called a cylindrical projection, and what's called a conic projection. So depending on the type of distortion that you want to minimize or the accuracy you want to maximize, it affects your choice of developable surface. This is something we spend quite a bit of time on in cartography classes, in computer cart, geography, GIS classes. Take, for example, the state of North Carolina, very wide or long east to west. They wouldn't want to use a projection for all their state maps that was centered on Kansas and minimized, U.S. nationwide, distortion. They want a map projection that gives the best view of North Carolina. So the Lambert conformal conic projection is the basis of that. It is a cone wrapped around the Earth, basically, that projects on North Carolina. And that cone, if you imagine, intersects North Carolina And there you can see the state is kind of its kind of best shape and area and minimized distortion. The next is the units of geographic coordinate systems on the Earth. What are we using? We're using GCS. It's a coordinate system based on angles. And so we can have any location on the Earth. We can measure that or describe that location with a coordinate pair, a latitude and a longitude. And those are measured in degrees. But we need a reference for the degree measurement. So we use the equator to measure angles north and south in terms of those are measures of latitude. And then we measure east to west from a central or primary meridian, the prime meridian, which goes through the Royal Observatory in London, United Kingdom. And we measure east to west relative to that semicircle. So basically the north and south pole are 90 degrees north and 90 degrees south. And the equator is 0 degrees north or south. You may see those plus represented as pluses and minuses. We'll talk about a little bit later. And then longitude is measured east in a positive sense, east of the prime meridian, all the way to 180 degrees. Now, choosing one of these map projections matters because all maps have distortion in them. The Mercator projection, created by Dutch cartographer Gerhardus Mercator, is great for navigation. It preserves the angular or directional accuracy of maps, but it sacrifices size and shape of features. So there you see a map of the conterminous or contiguous lower 48 United States, and Mercator's very sharp angles. If you were going to west from along the Canadian border on the 49th parallel, that is a straight line. Whereas if you actually use the other map projections, you have distortion in your progress, in your exploration or what have you. However, the Lambert conformal conic is really good at showing shapes and preserving like an accurate shape of features. So that's more likely what you would see in representations of the United States 48. Then you have the unprojected coordinates, which distort both of those. So we rarely would want to show those, but sometimes we do use unprojected coordinates. I have a note here about geodesy and what datums are. It's very important to know that we do need datums for the horizontal reference, so the prime meridian and the equator, but also for vertical. We need references for elevation and altitude. So here is a bit of discussion about the common datums. We use North American datum NAD, it's called 1983, and we're getting ready to shift to a whole new type of datum that was based on the satellites, GPS and other satellite constellation. But the older datums use things like a rock set, basically a metal plate set in stone in a ranch in the middle of the country in Kansas. That was the center from which every latitude and longitude was essentially measured in North Carolina or in North America for many decades. It wasn't really a reference just to geographic coordinates. It was used as a reference for projected coordinate systems that we're going to be talking about. These datums do have issues, and so very commonly people mistake them or enter the wrong one or think they're using one datum when they're actually using another. So huge problems can happen with that. You might see problems with construction engineering projects, problems with GIS and GPS users, and even things like people, digging trenches into underground utility lines and breaking water mains and electrical power transmission that's under the ground. Another note here is vertical datum. So I'd like you to check out the section that we use for sea level. So hugely important to Norfolk, but the United States and the world at large, seeing massive acceleration of sea level rise in the coming decades. We need to reference what sea level is when we record the elevations of things. And this could be a huge problem, even a practical problem. We don't want an aircraft carrier running aground as it comes into the Navy base. And so we need to know where we are and what time we are where in order to do safe navigation. And also for floods, being able to know where we are at our height relative to flooding from extreme rainfall or storm surges is huge practical value. So there's a little bit of detail here about there are various measures of tides, the sun and the moon creating tides across the earth, and knowing where you are relative to the high or low or the mean tide is very important. 2 or 3 projected coordinate systems I want to cover are UTM. And so UTM is huge. It's one of the first and most popular globally adopted projections and coordinate systems. It is a military-based grid reference system that kind of was created in World War I during the epic era of trench warfare. And it was much easier to make calculations using this. And you could have fine scale maps with just a lot better detail than using cumbersome latitude, and longitude, and degrees, and minutes and seconds that we'll see in the next unit. Essentially, the Mercator projection is a cylinder wrapped around the Earth with the features on the sphere mapped, projected onto that, and then it's unrolled. So here is a zoom view of one of the a prototype or anatomy of a UTM zone. There are 60 of these, 6 degrees wide in longitude, wrapped around the Earth. And actually there's one north and one south of the equator. And so each one of them has its own kind of prime meridian in the middle that is 0 meters north and south, and has a 500,000 meters east as a reference. So if I told you we were at 525,000 meters easting, the east value is measured in eastings, the north value is measured in northings, then you would know, oh, I'm east of the center of this UTM zone. States, we haven't really adopted the metric system commonly in the United States, and we go back to very commonly states have one or more of their own map projections and coordinate systems. They use feet. They are very similar to UTM, but they are unique to each of these zones within a given state. Virginia has a north and Virginia south. So there are characteristics. If I was to want to have GIS data from the state of Commonwealth of Virginia, it would very likely be delivered to me or downloaded in a digital file in Virginia state plane coordinates in feet. And that projection would show Virginia in a very nice shape and non-distorted area type of projection. Each of those would have a unique township number and range number referencing this. So there is, if you're from out Midwest or the Rockies or beyond, you will notice there's very often this Cartesian coordinate system nature, and the streets, the cities are all laid out on a grid system that reflects this. Here back east in the old colonial era in Virginia, we did not have that. And so that system called Mets and Bounds was used, mostly using references to features on the landscape, rivers and mountain ranges, creeks, and even down at the parcel or plat or scale of a deed for property, you would see a measurement description of that area based on landmarks, distances, and angles.